right, so we're picking up on slide 20 for the purple notes. This is kind of a review. I wanted a little bit of the graphing in this, so it's just the very hardcore basics when it comes to position versus time graphs. So should be pretty simple here, these first couple slides. And then we're going to talk about our next topic, which is acceleration. So you're going to notice that there is velocity, there's time, and so it's going to be really similar to the setup that we've already used, but now we're just kind of looking at it kind of one step further, I guess. So we really just have two topics left, acceleration, and then our final type of graph, which are velocity, purple, go to the purple, the velocity versus time graphs instead of the position versus time graphs. So really we're getting pretty close to the end of this unit. All right, so slide number 20, velocity we know can be interpreted graphically using our slope, which is rise over run. Because of the set variables on this type of graph, they match the same variables that are in the equation. There you go. There you go. That are in the velocity equation. Okay. So if we have our change in position divided by our change in time, that's going to be basically like taking our slope of rise over run for these type of graphs. Again, this is not new information. This is what the whole white packet was about, but just in more detail. Okay. Oh, my pointer is really moving quick today. Okay, and so here's basically kind of the summary. There's only two real main things you need to consider. One, what direction is the line headed? Up is some kind of positive velocity, downward slope is a negative velocity. So again, our positive meaning like forward, north, up, right, or east, and then down meaning our negative for backwards, down, south, left, or west. The next thing is that we need to see, is the line curved or is the line straight? How are the lines on most of your graphs for speed for the three-legged race? Were they perfectly straight or did they have some curve to them? I'm seeing some shakes for curve. Yeah, you probably weren't super consistent, like perfect cruise control as you were running. Some groups that went slower, they were a little bit more methodical, and so they might have been a little bit straighter or more consistent. More like that cruise control situation. So if we have, here's our three main examples. If we have velocity of a straight line, and all of these are straight, so they're all going to be like cruise control or constant. So this would be like object one moving at a constant positive. So an example would be a car on cruise control traveling at 55 miles per hour, maybe north or forward, east. Object two, the car is at rest, meaning flat line, not moving. So it's like a parked car or a car that's in park. All right, object three, moving with a constant negative velocity. So this is like a car going in reverse on cruise control for like 10 miles per hour. I don't even know if a car can actually, like if the cruise works in reverse. I don't know. Every time I see this, I think I'm going to have to try it, and then I always forget. But I don't know if that even is a thing. But you can imagine if you could do that, setting the cruise control going in reverse at 10 miles per hour. Okay, nothing shockingly new, right? Does that all sound familiar? All right, instantaneous velocity. So this is the velocity of an object at a set instant or a specific point in an object's pathway. So if I'm looking at a graph, that would be me putting a point on my velocity line or my curve or my straight line, possibly, right? And so the way that you do this is if you put the dot here, and then from there you make like a straight line coming off of that, or if you take 2 points, you could find maybe even like the average acceleration, or excuse me, the average velocity of this object. Right, and that's something that we'll do in our acceleration lab. You'll have 2 or 3 points, and you're going to connect the two endpoints to give an average acceleration. All right, but But an instantaneous velocity would be like a cop getting your speed on a radar gun. Obviously it's speed because he's not really worried about direction, but we know this could also be considered velocity if you would include that direction. Okay, so it's that point in time. If I'm on a 2,000-mile road trip and I have been following the speed limit the whole time, and I just happen to be going down a big hill and my speed gets up to 80 miles an hour instead of 70 miles an hour, and a cop is there and gets my speed of 80 miles per hour, do you think that he or she is going to believe, like, hey, I've been on this big trip, I haven't sped at all, I've been following all the speed limits? Well, I wasn't at that instant in time, right? And so just bad luck, at that specific instance, that's when the cop put the radar gun on my speed, okay? Okay, moving on to acceleration. So acceleration is the rate at which velocity changes over time. Sounds pretty easy. So when an object accelerates, its velocity or direction, or possibly both, have changed. Because if the variables are velocity and time, if you change the velocity, which would also mean giving you that option of maybe just changing the direction, so changing the sign, then that's also a way to change an object's acceleration. All right, so average acceleration is your change in velocity divided by the change in time, or the time required for that change to actually happen. So here's the equation. Average acceleration is final velocity minus initial velocity divided by final time minus initial time. Also, the easy way to think of this is our change in velocity over our change in time. All right, and so you can see we have a triangle. So if we're solving for time, we would cover it up and it's going to be velocity divided by acceleration. If we are solving for velocity, it'd be acceleration times time. So obviously acceleration is going to have its own unique set of units, a new type of unit that we haven't looked at yet. We'll come back to these videos in a minute. A typical one is going to be the meter per second squared, or the meter per second per second. And I'll kind of walk through what that'll look like where those units actually come from. So if you look up here, we said most of the time our initial velocities our initial positions and our initial times would be 0. Well, in this case, a lot of times our initial velocity is also 0. So if our initials are 0, then we don't need to do the extended version. We really haven't had to do that when we were calculating velocity. Now that we're going to be calculating acceleration, there are times when you're already traveling at a set velocity, so that would be the initial, and you would have to plug it into the extended version. All right, so up until this point, we haven't had to do the extended version, but there will be times if your velocity is not 0 to start with, or you started from rest or something like that, that you will now have to actually plug in the initial velocity. Okay, acceleration is also vector because it has velocity in it, so that's what makes it vector. You guys are really good at identifying that velocity is vector. I heard even people saying VV, remember SS for scalar and speed, VV for vector and velocity. All right, because velocity is part of acceleration, by default it makes acceleration vector as well. Okay, so here is a practice problem. A roller coaster starts at rest and speeds up to 50 meters per second over the course of 17 seconds. What is the average acceleration? So just like we always do, we are going to circle what we're solving for. All right, so what is it asking for in this problem? Anthony, what do you think? What's it asking for? What are we solving?
Acceleration.
Good, so we'll circle acceleration, and then hopefully it gave us 2 variables that we need. And so for solving for acceleration, the equation we'll use is our change in velocity divided by our change in time. We didn't have to rearrange that triangle equation at all. So now we're going to underline the information given. So we are given 15 meters per second. What is our second piece of information that's given there? Cool.
17 seconds.
Good. 17 seconds. Okay, so our velocity is 15 meters per second. Our time is 17, which is great because those are the two variables we need. So now we just plug them in. So we're going to take 15 meters per second divided by 17 seconds. And the number is 2.9. The units become the meter per second squared, because you're dealing with a second here and you're dealing with a second here. Because you have 2 seconds, you have to represent that as a second squared or a second times a second. And I'll work that out a little bit more tomorrow when we get to our calculations, kind of show that process. But you're always going to have a length unit divided by the time unit squared. That's what makes it different than velocity. And if you think about it, you have, your velocity over your time. So your time has to be represented basically twice with that squared value. All right, so velocity is the meter per second or some version of length divided by some version of time. That's what we already know. Now we're dividing that by time to get our meter per second squared, or some version of length divided by some version of time squared. Again, the units are still super important. So if acceleration is positive, then the object is speeding up. If the acceleration is negative, then it's decelerating. You need to include that negative sign so people realize, because speeding up at 10 meters per second squared is very different than slowing down at 10 meters per second squared. So including that negative sign is even more important than it's ever been. So getting things plugged into the equation is crucial if you're, so you don't mess up the sign. Okay, let's stop there. We've got a bunch of videos that we're gonna watch.